Hi everyone. In this particular video, what we're going to do is we're going to start discussing a new concept called hybridization. Now, you've probably heard about this concept in Gen Chem, but we're going to explore it a little bit more and use it to understand the bonding in organic compounds. But you could use it for understanding bonding in any compound for that matter, but we will be limiting it to organic compounds and specifically the second row elements like carbon, nitrogen, oxygen, and such. So what determines the hybridization of an element? So the hybridization of an element, this is determined by the number of groups. It is determined by the number of groups around an atom. Now, what's important here is what's defined as a group. A group is defined as other atoms which you could think of as bonds. And in fact, I'm going to be very specific here. Sigma bonds. Sigma bonds are the single bonds, okay? And we'll talk about these in a little bit more detail, okay? But the number of atoms or bonds plus lone pairs, okay? Plus lone pairs. That is what defines the number of groups around an atom. So that's how the hybridization of an atom in a molecule is determined. That's determined by the number of groups, which includes other atoms that it is bonded to, but we only count sigma bonds and lone pairs. Okay, so other atoms. In fact, if you think about from an atom standpoint, whether it's a sigma bond or a pi bond, well, there's no pi bond by itself, but whether it's a single bond or a double bond really doesn't matter. Okay, so it is atoms plus lone pairs. That's what we're looking at now. And what does hybridization tells us? It tells us the nature of bonding, okay? Which orbitals are used to form a specific bond. That's the information that we're going to get out of hybridization, this concept of hybridization. Okay, it would help us determine which orbitals are used to form a specific bond. That's the information that we get out of it. So that's sort of like a preview. Let's go into some of the details. And what I'll do is I'm going to discuss the sp3 hybridization first, and then we'll go into sp2 and sp hybridizations. Okay. And we'll also talk about why this is important and such. Okay. So to start off, we're going to discuss sp3 hybridization. And we'll also discuss the need for this. Why do we need to hybridize? You know, what is this concept of hybridization? So as an example for this, we're going to use the simplest organic molecule known, which is methane. Okay, methane has a structure that's like this. So let me explain some of the aspects of the structure, actually, the way I've drawn this structure. So in organic chemistry, and this structure is drawn in sort of, this is representing that carbon, the bonding around that carbon in 3 dimensions. That's what I'm trying to capture here. So in organic chemistry, when we draw a structure like this, the way we read this is any bond that's a straight line bond, that bond is in the plane of your board, or when you draw it on paper, it's in the plane of your notebook, you know. So essentially these two bonds, which are the straight line bonds, these are in the plane of the whiteboard. Okay, the hydrogen that's on a wedge, that hydrogen is coming out of the plane of the whiteboard, so it's pointing out towards us. So when I look at that structure, that wedge, so we call it a wedge bond, that wedge is pointing out towards us, and the dash bond is actually going behind the plane of the whiteboard. So we're treating the whiteboard as a 2D plane, and so the wedge comes out and the dash goes in. Okay, so let me illustrate this by using a model here. So okay, so let's say this is the methane molecule. Okay, and so this green here is the carbon atom, and the 4 hydrogens are at the ends here. So these are the bonds, okay? The black ones are the bonds. So essentially the way I've drawn this methane molecule is like this. So when you look at it, you have 2 hydrogens, this black one, okay, this black one and the black one at the top, these are in a plane. Okay, so they are in one plane. They are in one plane, these two. These two are in one plane, which is the plane of the whiteboard. And you have the hydrogen on the wedge, which is pointing towards you, and the hydrogen on the dash is pointing away from you. So that's how you're viewing this in 3D. Okay, these two are in a plane, that hydrogen pointing towards you, the wedge, and the dash pointing away from you. So that's how we read this. And it is not just for this molecule, it's for any molecule where the carbon is sp3 hybridized. And whenever a molecule is drawn using wedges and dashes, we'll be using this a lot in chapters 4 and then 5. Okay, so that's one thing. So we have a 3-dimensionality to the molecule, the way it's drawn. The other thing about methane is that all of these carbon hydrogen bonds, they are of equal length. Okay, and additionally, the bond angle here, this is a tetrahedral bond angle. Okay, so 109 degrees and 8 minutes. That's what the bond angle is. And now we can just approximate it to like 109.5 degrees. You know, that's what we usually do. So we can just say that this is 109.5 degrees. That's the tetrahedral bond angle. So, and every bond angle here is that 109.5 degrees. So going back to the model, essentially what I'm saying is this bond angle is 109.5. This bond angle is also 109.5. This here is 109.5, and that one is also 109.5. So all of those bond angles are 109.5. So now the question is, how do we explain that? Okay, I mean, using carbon, how do we explain this bonding? The fact that all the bond angles are equal, they are 109.5 degrees. And for a molecule like methane, all these bond lengths are equal in length. How do we explain that? And I'll sort of walk you through where the discrepancy arises. You know, where is the issue? So to talk about this, let's go back to carbon. And we've discussed carbon earlier. What we know is electronic configuration for carbon is 1s2, 2s2, 2p2. When we draw this as boxes, and I'm only going to draw the valence shell here, okay, it's the valence electron. So 2s2 and 2p2, okay. So we have a 2s orbital and we have 2p orbitals. Again, remember that, so this is 2s, and then we have px, py, and pz. Okay, these are all 2, 2, 2. 2px, 2py, and 2pz. So what we have is, we have a carbon with 4 electrons in its 4 valence electrons, and it needs 4 additional electrons to complete its octet. But if you look at this point, and so it has to share the electrons. We talked about covalent bonding. So this ground state, okay, this ground state electronic configuration of carbon cannot explain the bonding, because when you look at it, we have 2px, 2py, and 2pz is completely empty. And the problem here is these px, py, and pz, they are sort of showing the directionality of these orbitals. So when we think about coordinate axis, if we have, let's say, x, y, and z, the way we understand these px, py, and pz orbitals is the orbitals have some directionality. So when we say it's a px orbital, that orbital is aligned along the x-axis. Okay, a p orbital is dumbbell shaped. Again, something that you know from Gen Chem. So okay, a p orbital is dumbbell shaped, and essentially what's happening here is we have the lobes of the orbital that are along the x-axis, the plus x and the minus x-axis. Okay, so these are along the x-axis. That's why it's called a px orbital. Similarly, a py orbital is oriented along the z-axis. So there's one lobe along the py is oriented along the y-axis. So there's one lobe along the plus y, and the other lobe is along the minus y. Okay, and pz would then imply that the lobes are along the pz and the py. So there is one lobe around the z-axis coming here, and the other lobe is along the minus z. Now, there is nothing to the colors that I have drawn here. I'm just trying to show you how the p orbitals are drawn. I could just use black, and probably that's what I'm going to do like from here on. But it's just to show you that these are along the px, py, and the pz axes. And so what does that mean? The fact that these are along the px, py, and the pz axes. If the px orbital is along the x-axis and the px orbital is along the x-axis, py orbital is along the y-axis, what should be the bond angle between these two orbitals? One is along the x-axis, the other one's along the y-axis. What's the bond angle between them? That should be 90 degrees, right? And the same is true for all of these. They are all orthogonal to each other. That means the bond angles here for these orbitals, they should all be 90 degrees. For any of these orbitals, the bond angle is going to be a 90 degrees. So if carbon uses the px, py, and the pz orbitals, let's say, to form these bonds, okay, somehow share electrons with hydrogen and form these bonds. So if it uses the px, py, and the pz orbitals to share with the hydrogen atom, form these bonds, then these bond angles should be 90 degrees. But what we know is, from experiments, what we know is that bond angle is 109.5 degrees. And so that means that you cannot just explain the bonding based on this ground state configuration. And in fact, we can draw an excited state. Okay, so we can then talk about an excited state configuration. And what we're going to do for this excited state is we're going to excite an electron from the s orbital to the pz orbital. So then we are going to have one electron over there and one electron in each of the px, py, and the pz orbitals. So now we have 4 unpaired electrons. In fact, now this is a better situation because at least carbon has 4 unpaired electrons. With our ground state, we would have to, like, the 2 hydrogens would have to put their electrons into the same pz. So that was like really bad. Okay, so now we are in an excited state configuration where carbon has 4 unpaired electrons. Remember, when we draw Lewis structures of carbons, we draw carbon with 4 dots around it to show the valence electrons. So these could represent those 4 unpaired electrons. So let's say if carbon uses this excited state to form bonds with 4 hydrogen atoms, okay, to share electrons with 4 hydrogen atoms to give us a structure of methane, it would still have the same issue. The geometry around that carbon atom, since it is using px, py, and pz orbitals, that geometry should be 90-degree bond angles, right? There should be some hydrogens that are at 90 degrees to each other. And then we have a 2s orbital, which is like very different. These orbitals are not even of the same energy now. And which means that the bond lengths cannot be same because the bond lengths are determined by the orbitals also, the orbitals that are used. And so this is where this concept of hybridization comes in. Okay, and so essentially what we say is, or the way we explain this discrepancy is by saying that carbon takes, since carbon has to make 4 bonds, what it does is it takes these 4 orbitals and it undergoes a theoretical process called hybridization. Okay, and when it undergoes this process, what results is 4 orbitals, okay, and these 4 are called the sp3 hybrid orbitals. Okay, sp3 because it used one s type orbital and 3 p-type orbitals. So based on the number of s orbitals that were used and the number of p orbitals that were used, we get this name sp3 hybrid orbitals. So now we have 4 orbitals, and these 4 orbitals, they are all of equal energy, and they have the same shape. because earlier realized that the p, x, py, and the p orbitals in general, they were all dumbbell shaped. What's the shape of an s orbital? It is spherically symmetrical. So it's like a sphere, essentially. It's like a ball. So we had orbitals of different shapes. We had one orbital, which was a sphere, and we had other three orbitals, which were all dumbbells. But now through this process of hybridization, we've converted this one s orbital and three p orbitals into four. Okay, so there are four sp3 hybrid orbitals, and each one is now of equal energy and of the same shape. And realize that earlier they were not even of the same energy, because 2s is lower in energy than 2p. 2p is higher in energy. Okay, and you know how to do all of that based on Gen Chem. Okay, you learn all of that in Gen Chem. So now once we've got these four orbitals, I've written four sp3 hybrid orbitals. What does that mean? This first orbital is an sp3 hybrid orbital. This is also an sp3 hybrid orbital. This is also an sp3. This is also an sp3. So now there's no s or p's. They are all sp3, 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 sp3 hybridized. And since we had 4 electrons overall, they all contain 4 electrons in them. So now with this model, okay, once we have the sp3 hybrid orbitals, when you have 4 groups or 4 groups in space, the best way to arrange those 4 groups is to arrange them towards the corners of a tetrahedron, okay, which is this shape here, the one that we were looking at earlier. Okay, so that's tetrahedron. So this is a tetrahedral bond angle. So that's a tetrahedron. Okay, this is a tetrahedron. So at the bottom, it looks like, so if you remove this top, it almost looks like a pyramid, and then it has like something at the top. Okay, so that's a tetrahedron. So when you have these 4 sp3 hybrid orbitals, the best way to arrange those in space is to have them point towards the corners of a tetrahedron. So now this carbon, after hybridization, it's going to have 4 sp3 hybrid orbitals, and they have the same shape also, like I said. And so it takes these orbitals and basically concentrates the electron density on one end. So there's the low, it looks like a p orbital, but it's not really dumbbell shaped. There's more electron density on one side than on the other side. So this makes for a better overlap, actually. Okay, and usually when we draw it, we don't show this smaller lobe. It's difficult. It's there, but it's difficult to show. So we have one lobe here. Okay, maybe I'll keep it. Let's say why that's one, and then we have another lobe here. Now, when I draw it, they're probably not going to look the same shape and everything. Okay, but they are. And I'm going to make this sort of bold to say that this is an orbital that's coming out. So this is what becomes that wedge bond. And there's another one, which is like a dash. So that's another sp3 hybrid orbital, but this is what becomes the dash bond. So now carbon has 4 orbitals around it. In fact, I think my orbitals look really bad. Okay, something like that. It is hard to get a proper orientation. Let's say that's the best. Okay, so we have the 4 sp3 hybrid orbitals. These are the 2 that are in the plane. There's one that is a wedge, so it's coming out. The other one is a dash, it's going behind the plane. So, and all of these orbitals, they have 1 electron in them. Now, hydrogen, okay, the hydrogen is 1s1. That's the electronic configuration of hydrogen. So then we have, and 1s orbital is again spherically symmetrical. Okay, any s orbital is spherically symmetrical, and this orbital has one electron. So essentially what happens is these four sp3 hybrid orbitals, in fact, before we go there, so these orbitals, like I said, you have four sp3 hybrid orbitals, equal energy, same shape, and they are oriented towards the corners of a tetrahedron. So that means the bond angle that I've marked over there, this is sort of defined here. Okay, that sp3 hybridization defines that bond angle. And so all of these bond angles are 109.5 degrees. And these now overlap with, let's say, this is the 1s of a hydrogen atom. And it has one electron in it. Okay, all of them overlap with the 1s of a hydrogen atom. So that's a carbon, and these are your hydrogens. They use their 1s orbitals to form those bonds. So now, once we've developed this, we can actually talk about these bonds. Okay, we know how this bond or each one of these bonds is formed. So this bond here is formed by the overlap of an sp3 hybrid orbital from the carbon atom with a 1s orbital from the hydrogen atom. And the same is true for all of these bonds. Okay, so each of these bonds in methane is formed by the overlap of an sp3 hybrid orbital from carbon with a 1s orbital from the hydrogen atom. Now, at this point, I also want to mention about sigma bonds. You've learned sigma bonds versus pi bonds, but I think it's a good idea to review what a sigma bond is and how it's differentiated from a pi bond. So I hope in Gen Chem you learned that sigma bonds, they are formed by head-on overlap of two orbitals. So if this is one atom, it has an orbital that it is using to bond with something. That's another atom, it's using an orbital to bond with something. Sigma bonds are formed when they overlap head-on like this. So that's a very good overlap between the two atoms as they form that bond. And so what this means is the electron density. So this orbital contains electrons, this orbital contains electrons, they overlap to form the bond. And so what that means is the electron density in this bond is in the internuclear axis. So if this is one atom, if this is other atom, then the electron density is along the internuclear axis. Okay, that is what it means. Or let me show this slightly differently. So let's say if these are two atoms, they are using their orbitals to form bonds. So let's say if this is one atom, that's another atom. And if these are using their orbitals, these are the orbitals to form the bond. When they overlap, the electron density in that bond is between the two nuclei. It's along the internuclear axis. And that's what happens here. The electron density in this bond is along the internuclear axis because they overlap head-on. Okay, so that's a sigma bond. So what we're making here, this is a sigma bond. Okay, so that's the bonding in methane. But this is not limited to methane. It is applicable to any situation where carbon or another atom is sp3 hybridized. Okay, so let's look at another example. And we will not develop the picture itself, but let's just look at what hybridization is, what the hybridization is, and what the bonds are. So I'm going to draw two examples here just to drive home this message. So example one, we're going to consider this molecule ethane or ethane, and example 2 let's say that. Okay, so the first thing we're going to do is, again, I'm choosing simple molecules so that I can show the concept, how this works. But let's say if we think about hybridization for the carbon atoms, what's the hybridization of this carbon atom? To determine the hybridization, remember the hybridization has contributions from sigma bonds, or the number of atoms around it, plus any lone pairs. So if you look at this carbon, it is bonded to 1, 2, 3, 4 atoms. So whenever an element is bonded to 4 atoms, it is sp3 hybridized, because it needs 4 orbitals to bond with those elements. So that carbon is sp3 hybridized because it has 4 groups around it, which includes atoms and lone pairs. So 1, 2, 3, and 4. The other carbon also has 4 groups around it, 1, 2, 3, and 4. So this is also sp3 hybridized. Okay. So these are both sp3 hybridized. And so now this can help us understand the bonding in this molecule. How is this bond formed? That's a bond between an sp3 hybridized carbon and a hydrogen atom. So this bond is formed by the overlap of a carbon sp3 with a hydrogen 1s. So carbon's sp3 hybrid orbital, carbon uses an sp3 hybrid orbital to overlap with a 1s orbital from the hydrogen. So hydrogen always brings in 1s. And which orbital carbon uses, that information is coming from the hybridization of that carbon atom. Similarly, we can do it for this one. That's a bond between an sp3 hybridized carbon and a hydrogen atom. So this is also CsP3 plus hydrogen 1s. That's how that bond is formed. And I guess the most important one here, which is sort of different, is this bond. How is that bond formed between the 2 carbon atoms? This is an sp3 hybrid carbon. That's an sp3 hybrid carbon, or hybridized carbon. So this is a carbon sp3 plus another carbon's sp3. So 2 sp3 hybrid orbitals from carbon atoms overlap to form that bond. Okay. Similarly, we can do it for this atom here, and this carbon here is sp3 hybridized. It has 4 groups around it, 1, 2, 3, 4. The nitrogen atom is the 4th group. And now the nitrogen atom, what's the hybridization of the nitrogen atom? Hybridization is determined by counting the number of groups, which includes atoms plus lone pairs. So if you look at the nitrogen, it has 1, 2, 3 atoms plus 1 lone pair. So 4 groups total. So that means this nitrogen is also sp3 hybridized. Now we've already talked about bonding between carbons and hydrogens here. So that is the same. How would this bond be formed? This is a bond between a nitrogen, which is sp3 hybridized, and a hydrogen atom. So this is formed by the overlap of a nitrogen sp3 hybrid orbital plus a hydrogen 1s orbital. So that's how that bond is formed. How is this carbon-nitrogen bond formed? This is a bond between a carbon that's sp3 hybridized and a nitrogen that's sp3 hybridized. So this is carbon sp3 with nitrogen sp3. So that's how that bond is formed. So that's sort of an introduction to hybridization. Why do we need to hybridize? And some solved examples on how it helps us to predict bonding in these molecules. And what we'll see later is hybridization also helps us predict the structure. For example, we said that the carbon here is tetrahedral. Because it's sp3 hybridized, it has to be tetrahedral. Okay, so we'll look at that actually. Thank you.